So Bayes' theorem is mainly about inference. So let me do the basic Bayes' theorem. So for example, if you have events A, B, etc., we have, of course, the probability of A, it's something. Then the question is, if B occurs, then question is, what more can you say about A? About A, in other words, how to update our knowledge about, or our uncertainty or certainty about A. So in a way, so something happens here, and what more can you say about? So given that something has occurred, so this is where the conditional probability comes in, and so this is in a sense trying to infer something about more about A from this one. So it also goes with inference and so on. So of course the conditional conditional probability is key here. Conditional probability of A given B we write it this way. So this is going to be PAB divided by PB. This is the definition of complete conditional probability. And then we can, so it's easy to check that it actually this definition satisfies all the requirements, the three axioms of probability. So this is a legitimate probability of their intersection divided by B. So from here we first of all get on cross multiplying, you can rewrite PAB as PA multiplied by PB. PA given B multiplied by PB. And also if you write here PB given A, of course it will be, you flip A and B, that will be PBA, which is same as AB divided by PA. So from here if you cross multiply, we get the other relation, probability of B given A multiplied by PA. Now if I equate these two, they are the same. So we get probability of B given A is probability of A given B multiplied by PB over PA. Now, so this is actually Bayes' theorem. So the derivation is simple. And what the implication, I'm going to illustrate it through some examples. Sometimes we can go one more step and rewrite A in terms of, so you have B here. Let's say it is B1, B2, B3, BI, BN, etc. And A is somewhere here. So notice that the BI's form a partition, whole set. This is the whole set. And BI intersection BJ is empty. So that's what a partition. So the probability of course, this is the same as probability of S, which is 1. But these are mutually exclusive. So this is the sum of the BI's is 1. So that's why it's called a partition, because if you add up all the probabilities of B, it comes out to be the whole set 1. Now notice that A is somewhere, so any set A is of course lives in S. So A may have intersections with BI's, and so A itself can be written as A intersection union of all the BIs. And that's because this is the whole set. A intersection whole set is 1. So we can rewrite this as A BI. So if you do the distributive law, this is union of I equal to 1 through n. And consequently, a probability of A is the probability of union of A BIs, I equal to 1 through n. But these are all mutually exclusive sets, so that's the sum of the probabilities, I equal to 1 through n, probability of A BIs. But this one we can again rewrite using the conditional probability. So this is one way to rewrite A also. So if you take this and plug it in here, you can also write this as probability of any Bj given A is the same as probability of A given Bj multiplied by Pbj divided by Pa, but Pa I'm going to write it like this. So this is a another form of, it's the same thing, but another slightly expanded version or another version of the Bayes theorem. So, all right, so far it has been just juggling equations or simple equations. So let me do a problem to illustrate its power, especially about inference. So let's say we have two boxes. I'm going to call them B1 and B2. And let's say this has got two types of some devices or some items. Let's say this has got 100 items, this has got also 100 items. But in this one, let's say we know that 25 of them are defective. And here, let's say 10 of them are defective. So you may or may not know this fact, but just to solve the problem, let's set it up. So the boxes are identical because both of them have about 100 items. So the example is, or the problem goes like this. You have two boxes in a room. They contain 100 items each. And so the question is, what is the probability that someone goes into the other room, picks up one item at random. So an item is picked at random. What is the probability that it is defective? The item is defective. So I'm going to define D to be item is defective. So we want probability of D. So let's look at the problem. There are two. So someone goes into the other box, two boxes. So random means the boxes being identical. The person picks up either one of the, there is no bias, you pick up either one of the box. So we could say probability of picking either box from context is half, right? So let B represent, BI represent box BI is picked or selected. Then our conclusion is that boxes being identical, PB1 and PB2 is half, right? So this is a reasonable assumption. If one box was 3 times as big as the other one, maybe the person would go there, so you would change the probabilities in that favor. Remember, in quality control, of course, a box comes in, you have no idea how many items are, etc. But the way I have set up the problem, and you can see the usefulness of conditional probability now. If I know that the person picks up a ball from here, it is pretty, or item from here, it is pretty clear what is the probability of it being defective is. We argue simply there are 25 defective items out of 100. So that's going to be probability of D given given B1 is the number of favorable outcomes divided by the total number. Favorable, in this case, we are looking for defective. So 25 of them are defective. So that is 25 over 100 or 0.25. Similarly, the probability, if you know that we picked up, the person picked it up from box 2, there are 10 bad items divided by 100, that's 0.1. So this is sort of the a priori information about without performing anything, just from the given data. So now we could use this formula to find out PD. So if you plug in PD from that, so we can call this the total probability formula. So probability of D is probability. In this case, there are only two boxes. So box 1 and box 2 forms a partition because the items have to come from either one of this. So there n is 2. So this is PD given B1 multiplied by PB1 plus PD given B2 multiplied by PB2. So now, of course, if I put in the numbers 0.25 multiplied by half plus 0.1 multiplied by half, that is 0.35 divided by half. That's going to be 0.175. So that's the probability that an item picked at random is going to be defective. So now there's an interesting part to the second part. Interesting twist to this problem, and that I'm going to call it as the part 2. Suppose an item is picked up from the other room and you bring it over. So this is part A. So here we found out from the given data what is the probability that randomly a picked up item is defective. That's about 0.175. And part B is the item is, you pick up an item and you test the item. Item is tested and turns out to be, and of course it only has two possibilities, and turns out to be, let's say, defective. Remember, this is the fact now. So the question now is, what is the probability that it came from, let's say, box 1, that we can ask this question. So what we need is what is the probability that it came from box 1 given that the item is defective. So this is box 1. Item is defective. So this is what the problem is asking for. So you the tested item turns out to be defective. So that's the new fact which we didn't have before. So that's a result of an experiment. So question is, can we update our knowledge about which box it came from? Previously, without any data, all we could say is there's a 50% chance it came from box 1. But let's see what it is now. So this is where the Bayes theorem is useful. So I'm going to use, so just use B is here, instead of A, instead of B, use B1. Instead of A, use D. So this reads PD given B1 multiplied by PB1 divided by PD. And we have all the numbers here. PD given B1 is 0.25. So this is 0.25 multiplied by 0.5 divided by 0.175. So this is this is going to be 0.25 divided by 0.35, so that's 25 divided by 35, that's 5 divided by 7, so that's going to be about 0.7, right? So 0.71, something like that. All right, so you see the big difference. So the experiment has allowed it to conclude that most likely it came from here, because previously we could only say that it came from either one with equal probability. Now that we turned out to be defective, of course common sense also says it must have come from box 1 with more defective items. But what the Bayes theorem tries to help us is to make that quantitative. Rather than say that it is more likely it came from here, how much more likely is precisely answered here. So you get a number. So if this is, actually this is only 0.7. If it was 0.99, then you know it's almost sure, etc. So what the Bayes theorem tries to help us is to quantify our usual notions, because even common sense says, of course, if it is defective, it is most likely came from B1. And what is additionally done here is making that statement more precise. So this is an example. And this is what I mean by inference. So we have inferred that with some accuracy, how much more likely that the item came from box 1.